let's dive into a really fascinating family of chemical compounds. Now, you've probably never heard their family name, but I can pretty much guarantee they are all around you. In some cases, they're even inside you, doing some incredibly important jobs. So, to get started, let's see if you can solve a little chemical mystery.
So here's a bit of a riddle for you. What could a powerful drug that fights typhoid fever, a hormone your body absolutely cannot function without, and a compound that makes modern surgery possible, what could they all possibly have in common? I mean, on the surface, they seem completely unrelated, right? But chemically, they share a secret identity.
And here's the big reveal. All three of these powerhouse molecules, we're talking chloramphenicol, thyroxine, and halothane, they all belong to this special class of compounds called organohalogens. And they're just amazing proof that one tiny change to a molecule's structure can have absolutely world-changing effects.
Okay, so here's our roadmap for today. To really get a handle on this, we'll start by figuring out what these hidden helpers are. Then we'll build out their chemical family tree to see how they're all organized. After that, we get to the really fun part. We'll explore the great chemical swap that makes them so reactive, uncover the mind-bending mirror image mystery of their 3D shapes, and finally, look at the double-edged sword of why they're both so useful and so stubbornly persistent.
First up, the hidden halogen helpers. Let's get right to the core of what these molecules actually are.
You know, the core idea here is beautifully simple. You start with a basic hydrocarbon. That's just a molecule made of carbon and hydrogen atoms. Then you just swap one or more of those hydrogens for a halogen atom. You know, one of those elements from that special column on the periodic table like chlorine, bromine, or iodine, and that's it. That one simple swap creates an organohalogen.
Now, this big group splits into two main families. And the difference is all about the type of carbon atom the halogen decides to attach to. For haloalkanes, the halogen is bonded to a carbon that's part of a simple chain with only single bonds. But for haloarenes, it's attached to a carbon that's part of a special, super stable ring structure. It might seem like a small detail, but trust me, this one difference completely changes how they behave chemically.
Okay, up next is a chemical family tree. With so many possibilities, chemists obviously need a clear way to sort and name all these compounds, so let's see how they do it.
It really just boils down to asking two simple questions. First, how many halogens are there? If there's just one, it's a monohaloalkane. Two, it's a dihaloalkane, and you get the picture. Then you ask the second question, where exactly is that halogen attached? And the answer to that one, well, it adds a whole new layer of detail.
This is all about the neighborhood that the carbon atom lives in, the one holding the halogen. If that carbon is connected to only one other carbon, we call it primary. If it's connected to two other carbons, it's secondary. And if it's connected to all three, you guessed it, it's tertiary. Now, this little detail might seem minor, but it becomes incredibly important when we start talking about chemical reactions.
And see, that classification system really matters because it helps us predict how these molecules are going to react, which brings us to our next section, the great chemical swap. This is where the real action happens, and we'll see what makes these molecules such perfect little building blocks.
Okay, the key reaction they love to do is called nucleophilic substitution. It sounds fancy, but let's break it down. A nucleophile is basically a molecule that's loaded with electrons, so it's always looking for something with a positive charge. And in our haloalkane, the carbon attached to the halogen is a little bit positive. So boom, the nucleophile is drawn to it, it attacks, and it kicks the halogen right out, taking its place. It's just a simple, elegant.
Now, what's so cool is that this swap can happen in two different ways. The first is called the SN2 reaction. The 2 here means two molecules are involved in the most important step. You can see the incoming group attacks the carbon from the back. At the exact same time, the old group is leaving from the front. It's a single, perfectly coordinated one-step dance move.
But there's another way, the SN1 reaction. Here, the 1 means only one molecule is involved in that key slow step. Think of it like a 2-act play. First, the breakup. The halogen just leaves, all by itself. This creates a flat, unstable, positively charged molecule called a carbocation. Then comes Act 2, the rebound. The new nucleophile is totally free to just swoop in and attack that carbocations to form the final product. It's less of a coordinated dance and more of a messy breakup followed by a really quick rebound.
And this brings us to one of the most fascinating and frankly beautiful ideas in all of chemistry. The mirror image mystery. This is where we see why the three-dimensional shape of these molecules isn't just important, it is absolutely everything. A really great way to understand this is to just look at your own hands. Go on, hold them up. They are perfect mirror images of each other, right? But now, try to place your right hand perfectly on top of your left so that your palms and fingers line up exactly. You can't do it. They don't match. This property of being a non-superimposable mirror image is called handedness, or to use the proper chemical term, chirality.
And believe it or not, molecules can have this exact same property. Whenever a carbon atom is attached to 4 different groups, that carbon becomes what we call a chiral center. And this means the molecule itself now has a handedness. The molecule and its mirror image become just like your left and right hand. Chemists call these pairs enantiomers. They have the exact same parts, but their 3D arrangement is fundamentally different.
So, how do our chemical swaps affect this handedness? Well, let's think back to that one-step SN2 reaction. Because the new group can only attack from the back, it forces the other 3 groups to flip over to the other side. The whole arrangement is completely inverted. The best analogy is to imagine a strong gust of wind hitting your umbrella and turning it completely inside out. Chemists call this an inversion of configuration.
Okay, so what about the 2-step SN1 reaction? Remember that flat carbocation that forms in the middle? Well, because it's flat, there's no front or back side to attack anymore. The incoming group has an equal 50-50 chance of attacking from the top or from the bottom. And the result? You get a perfect mixture of both the left-handed and right-handed products. This process is called racemization, and it creates a mixture that has no overall handedness at all.
Finally, let's bring all this amazing chemistry back to the real world with our last section, useful but persistent. This really is the double-edged sword of these remarkable molecules.
As we saw right at the beginning, the applications for these compounds are just everywhere. From life-saving antibiotics and anesthetics to industrial solvents and the raw materials for countless products we use every day, their versatility is a cornerstone of modern life. They truly are all around us.
But here's the catch. The very thing that makes them so stable and useful, that incredibly strong carbon-halogen bond, also makes them unbelievably stubborn. Many of these compounds are highly resistant to being broken down by natural processes, like the bacteria in soil, and that means they can persist in the environment for a very, very long time.
And this really is the central challenge, isn't it? We've seen their simple structure, their complex reactions, and their mind-bending 3D shapes. We know they are powerful enough to save lives, but we also know they can stick around long after their job is done. So the critical question we're left with is this: how do we balance the incredible power of these molecules with their lasting impact on our shared planet? Well, that's the puzzle for the next generation of chemists to solve.